Hi, everybody. So I'm just going over the John Smokestack case study here. So basically, John Smokestack, 60-year-old male, has a 40-pack-year history of smoking. We would assume that he has COPD. So just as a review, COPD is chronic obstructive pulmonary disease. It comes in two major varieties. You have chronic bronchitis and emphysema. Usually people with COPD have a combination of both chronic bronchitis or emphysema. With chronic bronchitis, you have narrowing of the bronchioles due to long-standing inflammation of those airways. And then with emphysema, you have a breakdown of the elastic fibers surrounding the alveoli so that they are not as compliant, meaning that they lack the ability to retract back on themselves during exhalation. And as you have learned in lecture, exhalation is mostly a passive process, whereas inhalation is really driven by the diaphragm and accessory muscles of inspiration. Exhalation is mainly due to the contraction, or the recoiling is a better term, of the elastic fibers surrounding the alveoli. So if you break down those elastic fibers, then you're going to have a more difficult time getting the air out. Likewise, with chronic bronchitis, if you're narrowing those airways, the big strong muscles that allow you to inhale have no problem overcoming the resistance that you get from the air coming in to those airways. But the problem is now when you get to get the air out, you have to rely on the passive process of exhalation, and you just don't have as much power to exhale that air through those narrowed airways. So the common denominator is, whether you're dealing with chronic bronchitis or emphysema, is you have trouble getting the air out when you exhale. That's where the term obstructive in chronic obstructive pulmonary disease comes into play. Chronic obstructive pulmonary disease literally means that you have chronic air obstruction, meaning you have trouble getting air out. All right, so your problem is with exhalation. So remember, the forced vital capacity or vital capacity is taken when you ask your patient to inhale as much air as they possibly can, and then at that point, that's your new zero. That's your starting place, and then from that point, you ask them to exhale as much as they possibly can. So the forced vital capacity or vital capacity is a volume that you take when you ask the patient to exhale as much as they possibly can after a maximal inhalation. So you're testing their ability to exhale air, basically. Now, on top of that, we have a new term added, which is the FEV1. The FEV1 is basically the amount of air that you can get out of your lungs when attempting a forced vital capacity within 1 second. So usually it takes a little bit longer, just a little bit longer, to exhale a maximal amount of air while attempting your forced vital capacity. So the amount that you're able to get out within the first 1 second of attempting that forced vital capacity is your FEV1. And then the amount that you can get out in 2 seconds is your FEV2. The amount that you can get out in 3 seconds is your FEV3. So for normal healthy people, they can usually get out their full forced vital capacity or exhale their full forced vital capacity in less than 2 seconds. So their FEV2, their FEV3, their FEV4, it's all going to be the same amount. All right, it's just going to be just slightly more than their FEV1. But with people with COPD, like John Smokestack here, as we presume, it's going to take a lot longer to get that air out. All right, so their forced vital capacity may not be a short, it might be a, and it's going to take a lot longer for them to belt out that forced vital capacity. So that FEV2, FEV3, FEV4 number is going to be more meaningful. They may actually be different numbers. And we're going to see with our Vitalograph down at the very bottom that that, in fact, is the case with this particular individual. So what we're going to start off with is we are going to predict his normal FEV1, or I'm sorry, his FVC rather, his forced vital capacity based on the prediction nomogram or nomograph. So let's go down to our predictive nomograph, and it looks a little bit different than the nomograph we saw at the first exercise, but no need to panic. Nomographs come in different shapes and sizes, all right, but it's the same concept. So we're going to take his height and his age, which are the lateral columns here. So we got to go back up. I don't have this committed to memory. So we see his height is 5'8", and his age is 60 years old. So let's see. We have to find, we have to convert this in terms of inches. So if you're 5'8", then 5 times 12 equals 60, then plus 8. So 68 inches is his height. So let's notch 68 inches right here. Gotta get the pen working. So I'm going to notch right here on the height column, 68 inches. That's his height. And then we're going to go over to the age column, and he's 60 years old. And I have my straight edge here. Oops. And we're going to draw a line. Oops. There we go. Sorry, it's hard to manage the straight edge with these iPads. I think the computer gets confused when it detects, the screen that is gets confused when it detects this large object. And as a result, that overrides the pen tool. Okay, let's see how I can do this. Worked before, okay. Not the straightest line in the world, but shoot. Let's just try this one more time. What I should have done is just drawn it out on paper. There we go. There we go. All right, so where do we intersect for our FVC, predicted FVC? So right here. So you can see that the FVC is in terms of liters. So these little notch marks right here are going to be 1/10 of a liter or 100 milliliters. So we can see that his predicted FVC is going to be 4.3 liters. So that's what he should be. So again, we're going to write in 4.3 liters, which translates to 4,300 milliliters. Now we're going to calculate his predicted FEV1. So we go to the FEV1 column and find where the straight line intersects. And so we see that this is going to be 3.2 liters. So we're going to put in 3.2 liters here, and 3,200 milliliters is that equivalent. Okay, so now we're going to look at his Vitalograph, which is down here at the bottom. So the Vitalograph is basically the reading from his actual pulmonary function tests. And this is how it is arranged. We have air volume in terms of the air that he's exhaling, and that's the y-axis, and then the x-axis is going to be time. So what we're seeing with this graph is the amount of air that he is exhaling over time. So this is a little bit different than the lung volumes graphs that we showed you on the PowerPoint. In the lung volume graphs that we showed you in the PowerPoint, we show both inhalation and exhalation. But the Vitalograph is just showing the amount of air that he is exhaling after he takes his maximal inspiration. All right, so this is the starting point right here where I'm marking with the red dot is after taking his maximal exhalation. And in reality, the computer programs that the pulmonary function testing equipment uses can switch these graphs back and forth to different formats. This just happens to be the format that we're showing you. It's just a little bit more user-friendly for obtaining these FEV1, 2, 3 values, etc. So remember, we said that the FEV1 is the amount of air that you can get out in 1 second while attempting your forced vital capacity. So here's 1 second right here. So now we follow up to find the corresponding volume of air, and we see that this corresponds with a volume of air of 1 liter, only 1 liter. So what did we say his predicted FEV1 is? It should be 3.2 liters, but it's only 1 liter. Why is that? Because he has COPD. He has trouble getting the air out. He probably has a combination of chronic bronchitis, the narrowing of the bronchioles due to inflammation over years, and emphysema, the breakdown of the elastic fibers surrounding the alveoli. Both of those factors work together to make it difficult for him to get air out, to exhale. His FEV2 then is going to be the amount of air that he can get out in 2 seconds. So we go up here to find the corresponding volume with 2 seconds, and that's 1.5 liters. So his FEV2, actually let me write this in. So this is FEV1 is 1 liter. His FEV2 is going to be 1.5 liters. And his FEV3 is going to be 1.8 liters. His FEV4 then, this is where the line finally plateaus. So this is the maximum amount of air he's able to get out. He gets out by the time we get to the FEV4. His FEV4 is going to be, actually, you know what? I just misstated. I'm getting ahead of myself because I'm doing this by memory and not counting the actual notches here. So his FEV3, if I actually follow this back, is actually going to be 1.7. I'm sorry for that, guys. So the FEV3 is going to be 1.7. His FEV4, rather, is going to be 1.8. So this is the FEV4 right here. Actually, you know what? Maybe if I use different colors, it would help. Let me get rid of all these FEVs. And use different colors. So let's do nice complementary color here. Do the aqua. So again, 1 liter, this is the FEV1, 1.5 liters, this is his FEV2, 1.7 liters is the FEV3, and then the 1.8 is the FEV4. All right, so his FEV5 is still going to be 1.8 liters. His FEV6 is going to be 1.8 liters. His FEV7 is going to be 1.8 liters, because once we get to 1.8 liters, that's the maximum amount of air that he can get out with his forced vital capacity. All right, so now let's go back up to our diagram right here, or I'm sorry, the worksheet. Actual FEV1 is going to be 1 liter, which is the same as 1,000 milliliters. The actual FEV3 is going to be 1.7 liters, which is 1,700 milliliters. And his actual FVC is going to be 1.8 liters, which is 1,800 milliliters. So to make the test results easier to understand, test results are given as a percentage of normal. So in order to be able to make sense out of the FEV1 that's actually measured in terms of the patient's FEVC, what we do is we divide the FVC into the FEV1. So that's ultimately the most useful clinical measure of these two related terms, and that's what we're working our way up to. But we're going to start off by looking at each of these two parameters, FVC and FEV1, individually. So what we're going to do is we're going to compare the patient's actual FVC to the predicted FVC to see how close his actual FVC comes to the predicted FVC in terms of percentages. So what percentage of his predicted FVC was he able to accomplish? That's basically what we're measuring right here where we start off. And we're going to do the same thing for the FEV1 and then work our way up to calculating the all-important FEV1 to FVC ratio. That is his actual FEV1 to his actual FVC. So actual FVC to predicted FVC, we said his actual FVC is going to be 1.8 milliliters, and his predicted FVC is going to be, actually, you know what, I'm realizing now we don't have slots to insert these individually. So what I'm going to do is I'm going to just pencil this in alongside these designations right here. Okay, so the actual FVC we said is going to be 1.8 liters, and his predicted FVC is going to be 4.3 liters. So 1.8 divided by 4.3 is what? Getting out my calculator. 1.8 divided by 4.3 equals 0.418, so let's say 0.42. So if you multiply 0.42 times 100, you end up getting, actually, this is where we insert the slot. Okay, so we multiply 0.42 times 100, and that equals 42%. So his FVC, his actual FVC, is only 42% of what we would expect it to be. So not too great. He has a lot harder time getting air out than you would expect for someone his age and height. So now let's do the same thing for the actual FEVC or FEV1 to his predicted FEV1. His actual FEV1 is 1 liter, and his predicted FEV1 is going to be 3.2 liters. So when we divide 3.2 into 1, what do we get? Or another way to say it is 1 divided by 3.2. 1 divided by 3.2 equals 0.3125. Let's just say 0.31. Round it. And then we multiply that times 100 and we get 31%. So his actual FEV1 is only 31% of what we would expect it to be. All right, so now we get to the FEV1 to FVC ratio, which is the most important and clinically relevant of these ratios that we talk about here. This is the one that actually has prognostic value for which stage of COPD you're at. So his actual FEV1 is 1 liter, easy, and his actual FVC, actually, forgot the blanks aren't here. Should redesign this so we have blanks for all of these. So the actual FEV1 is 1 liter, and his actual FVC is going to be 1.8 liters. So 1 divided by 1.8 is 0.555, so we'll round that to 0.56 times 100 equals 56%. So he's only able to get out 56% of his maximal FVC within 1 second. A normal person should be able to get at least 80% of their FVC out within 1 second. Now, the amount of air that you can get out in 1 second, that is your FEV1, compared to your total amount of air that you can get out with a forced vital capacity, is used to grade the progression of COPD. So, for example, if you can get out anywhere from 100%, which not many people can, but you could, to 80% of your FVC within 1 second, then you are normal. For people who have FEV1 to FVC ratios that range from 80 to 50%, then they are said to have mild COPD. For people whose FEV1 ratios, or I should say more specifically FEV1 to FVC ratios, sorry, these are tongue twisters, range from 50 to 30%, these people are said to have moderate COPD. And for people whose FEV1 to FVC ratios are less than 30%, this is when we get to severe COPD. And once you drop down below 15%, then that's end-stage COPD. So those are people who are in hospice as a result of their COPD. All right, so we can see that John's smokestack is right along the path to going from mild to moderate COPD. And the way it usually goes is as you age, the problem becomes, exponentially worse. So once you get age going against you, once it's not on your side anymore, the problem tends to exacerbate with an exponential progression. All right, and that's why it's so important to stop smoking as soon as you can to be able to have any advantage on your side that's possible in stopping or stemming the progression of this disease. All right, so that's the relevance of all of this. It's really not too bad. It's not as intimidating as it looks. All right, everybody. So I will see you soon.